Not today. Twice in a row, I know. All right. Could have, but I hope I would have noticed. All right. It's 9th week Friday. Can you believe it? I mean, yeah, and we have this lecture and like 2 more lectures left, and then we got a test on Friday, I guess, next Friday. I will have to talk about, I'm still trying to figure out what to do for the 3rd test. I'll say this now, and because this is my intention. My intention is to make test 3 gentle, okay, and nice, and make it like a lower stress exam, okay, if there's such a thing, right? Now, yeah, there is, okay. I mean, I don't know. It's not going to be low. I don't want to say no stress or low stress, but I'll try to make it lower stress, okay. And so I'm working on that. I'm trying to figure out some good things to do there. I want to put together a homework 6. I know you guys don't want that, but I want to do it because I'll make it due. I'll give you at least a week, so it'll be due probably during 11th week, okay. And I don't know. I think there's some cool stuff we can do with the Gibbs sampler that I want you guys to see. Okay. Huh? So anyway. So test 3 will be, quote, gentle, whatever that means. And then homework 6 will be created as a kind of a neat application of the Gibbs sampler, and then I think we'll start there. Okay. I don't know, because a lot of you guys are graduating, and I don't want to overburden you guys with what's that? Too late? I know. So, well, I guess I just don't want to pile onto it. So, just adding a little bit, okay? Because I am required to have some form of a final evaluation. I can't. Huh? A take home. Yeah. Well, the students have broken my hearts too many times with take home exams. So. Yeah. There's so. Okay, we left off on Wednesday talking about the beta binomial model. Yes, question.
I had a question about homework 5.
Homework 5.
Since we don't have to post the code for the decode, do we have to post the code for decoding those
No,
messages?
no.
So that it feels weird if I had one of them I got decoded perfectly. Should I just put it twice in the decoder true message?
Yeah.
That's fine.
Yeah. If your max decode got it perfectly correct, then awesome. I would say most cases it doesn't do it perfectly, but it gets pretty close, right? I don't know. I think mine says but I don't want to be sad, but it's it's mad, right? So, or whatever. I don't want to go among the mad people or sad people or something, right? So I mean that's you can see how it gets mixed up, and you get some other nonsense word somewhere in there. So there you go. Okay. Yes.
You can put quotations on a real answer.
Yeah. It's the exercise was mostly to force you to try out the code and hopefully think it's kind of fun. Maybe it wasn't fun and just frustrating, but I don't know. All of these things, we're learning all of these fairly powerful concepts, but we have to, when you teach them and introduce them to be understood, you start off with these simple toy examples, and unfortunately, when you do the toy examples only, you kind of lose. You forget how powerful this stuff is. Someone's doing gardening out there. So the Gibbs sampler, we're doing it to sample from the bivariate normal in your homework, and it's a perfectly valid method or perfectly valid use of the Gibbs sampler, but there's we can do super awesome stuff with it that would not be possible with our classical methods. Can we close that door? Is it closing? There. Okay, it's a little bit better. Okay. It must be right outside the window. Yeah, that's okay. We do have a beautiful campus, so I'm thankful for everybody who keeps it beautiful. No thanks to people who litter, or smoke and throw their cigarette butts on the roof of the 9th floor. I know, right? No, okay. All right, anyway. Okay, so anyway, we're talking about beta binomial. What we're doing is we're saying, in the homework we did this baseball example, and we said our prior distribution is a beta distribution where alpha is equal to 81 and beta is equal to 219. And it was a little bit arbitrary how we selected those numbers, and we just said we selected those numbers in that baseball homework example because the resulting beta distribution looks kind of like what we expect the distribution of batting averages to be, centered around 20-something%, with a high of around 35 and a low of around 20%, something around there. That was the prior distribution that we gave, and that was that. And we said, well, you know what? I don't want to just arbitrarily pick alpha and beta. I want to estimate the values for alpha and beta as well, okay? And so we can do that, and we just have to create the entire joint posterior distribution of all the parameters we're trying to estimate. Theta, alpha, beta, and y. And we said, this joint posterior distribution, theta, alpha, and beta, given our data y, is going to be proportional to the likelihood of the data given the theta values, proportional to the theta given the alpha and beta values, multiplied by the prior on alpha and beta, okay? And again, there's questions like, well, how do we pick the prior for alpha and beta? Well, instead of having another distribution that has its own parameters that makes the model even more complicated, we're going to pick an uninformative prior for alpha and beta. And we're going to just say, basically, all values of alpha and beta are possible. Well, in this case, all positive values of alpha and beta are possible. And so we're just going to have basically, the prior distribution of alpha and beta is just going to be a constant, okay? Technically, the constant is 1 over infinity, which is technically 0, but because this is an improper prior, it's not one that integrates to 1. But we're going to just say all of these values of alpha and beta are equally likely. And so basically, the joint posterior distribution of everything is just going to be proportional to these first two terms. Okay? And we said when we do the Gibbs sampler for this, there's going to be a ton of parameters to actually estimate. So we'll take a look at some baseball data that I've drawn from a data set. And I think there's something like 436 baseball players that are going to be represented. Okay, each of those 436 players, we can imagine that each player has a true hidden batting average. That value is hidden from us, and we can only get an idea of what their true batting average is by seeing how often they are successful at hitting the ball. Okay, but you could have some Ty Cobb who has the highest batting average of all time, career batting average of all time, maybe 0.36 or something, and that's their theta. and we only get a hint of what that is by seeing how many times did he go up to bat, how many times did he get a hit, okay? And then, there's another player, maybe their true batting average is 25%, okay, 0.25, 250, and we only get a hint of what that is by seeing how many times they go at bat and how many times they get a hit, okay? So we have to look at the data to kind of infer what these values of theta are. And because we understand the relationship between the beta and the binomial distribution, we are able to draw sample a value of theta directly from the full conditional distribution given alpha and beta and our data values. And we said, the posterior distribution of theta given alpha, beta, and our data is going to be alpha plus the number of hits and beta plus the number of misses, basically, okay? And I'm hoping this part is familiar enough to us because we've seen this beta binomial thing, I don't know, a few times already, right? Okay. And then the other part was, okay, how are we going to sample alpha and beta themselves? Okay, alpha and beta, is going to be proportional to this. Okay, technically we could do the math to try to derive the full conditional distribution of alpha and the full conditional distribution of beta given all of the other parameters, and it's possible. It's not an intractable math thing, and you can see the math being done. But I just want to kind of illustrate that sometimes the math gets complex, and that's okay. You can almost avoid these tough situations by using the Metropolis algorithm. You just say, well, based on Bayes' rule, I know it's going to be proportional to this, and I can factor that out, and we have this, and we're going to basically just use this using Bayes' rule and say it's proportional to this, and because I know it's proportional, I can use the Metropolis algorithm where even though this thing doesn't integrate to 1, because the acceptance ratio will cancel out, whatever normalizing constant we have, we can get the value that we need. Okay, does that make sense? So I've coded this up, and I want to kind of show you the code that I've written for it. Okay. Oh, I have the tumor data, but we'll start off with the baseball data. Okay. So there's something known as the Lawmen Database, and this has a whole bunch of baseball stats. And let me just do like data batting. Okay. And if I ask for the dim of batting, there's 102,816 rows. Okay, so this is each baseball player every single season has a row in the batting table. Okay, and that's just going to be too many numbers for us to try to estimate. So I just arbitrarily said let's look at the year 2010. Okay, and I'm going to basically subset to just players who played in the year 2010, who played over 40 games, and who had over 50 at-bats, okay? And this will help eliminate non-batters, people who are kind of like reserve players, because in baseball, you have a 40-man roster, okay? There's 40 people technically on the team, but, only 9 people go on the field. And so, a lot of those players, they suit up, but they don't actually play. Some of them are just pinch hitters or, relief pitchers or things like that, and they may only play a few games. So by saying we only want games over 40, this will reduce it because there's 162 games in a season, and so this will make sure we're kind of getting people who have a fair amount of games, and then the number of at-bats over 50 to kind of filter out relief pitchers and pinch hitters and stuff. Okay, so we could take a look at y, and I've got 436 values. These are how many different hits we've had, and then n will be the number of at-bats. And we've got a lot. And I can kind of just create a plot of the density of y divided by n, okay? And this is kind of our empirical distribution of the batting averages for these 436 players. So there's a lot of, most of the batting averages are somewhere between 20 and 30-something%, and this is kind of our empirical distribution for the different batting averages we've seen. Okay, but keep in mind that the vector y is the number of hits, it's a count, and n is the number of at-bats, it's also a count. Okay, for the sampler, I'm going to say, all right, how many values do I have to estimate? 436. We got 436 players. And so that means all 436 players have their own theta value, the theta being their true probability of getting a hit when they step up to bat. Okay. And then again, we're going to we want to estimate alpha and beta. And so we're, rather than saying my prior distribution has alpha 81 and beta distribution has beta 219, I'm just going to pick some purposely terrible numbers, and we're going to use these as just starting values, and we're going to try to sample values of alpha and beta. Okay, and I don't know, let's do 15,000 iterations. This will take a little while to run. Okay. AB is going to be a matrix of all the different alpha and beta values I'm going to capture. Okay, so I'm going to run 15,000 iterations. So I'm going to have a 15,000 by 2 matrix, a matrix of 15,000 by 2, and that's what we have. Okay. Within the sampler, the Gibbs step is basically I'm going to sample a theta value from our full conditional distribution. Okay, so I don't have to worry about proposal and acceptance probability. I'm sampling theta directly from the conditional distribution using the beta, where the shape parameter is the original alpha plus the number of hits, and beta plus the number of misses. Okay, which is what we understand to be. Okay, but then for the alpha and beta portion of the sampler, because we want to sample values of alpha and beta, we need to have proposed values, and we're going to use the Metropolis algorithm to decide whether or not to accept those values. Okay, so to propose, I created a function that takes our current values of alpha and beta, and it's going to use a normal distribution centered at alpha and beta. So I'm going to draw one random normal value where the mean is currently set to alpha and the standard deviation is set to whatever standard deviation I specified. Default value is 1. Probably for this thing I'm going to use a larger standard deviation. Okay. I throw in this max 0 because technically the normal distribution can return a value that's negative, but you can't have a negative alpha or beta in your beta distribution. Alpha has to be at least 0 or something. So we're gonna so max 0 makes sure that if I draw a negative number, it will at least return 0. Okay. Same thing with beta. Okay, so we're just drawing a random value of alpha and beta centered at our current value of alpha and beta. So we got A prime and B prime, and so propose will return A prime and B prime. Okay, and then to calculate the probability, our probability is proportional to y given theta and theta given alpha and beta, okay, multiplied by that. And so this is a product, and so there are 436 values that we've observed and 436 different theta values. So basically I've got binomial probabilities using the vector y, the vector n, and the vector of theta values that we have. Okay, and then we also have the distribution of 436 theta values given our current choices of alpha and beta. And so this value is a bunch of beta probabilities. Okay, so this is going to be, so technically, how do we do this? Okay, so so this thing is going to be a product of basically beta probabilities, beta of theta given that alpha is equal to alpha and beta is equal to beta. Okay, so we have the product of all of those, and this one over here is going to be basically the product of a bunch of binomial probabilities of, you know, what's the binomial probability of y given an n and, you know, your theta value. Okay, I know that's hard to read, but and so these are products. Okay, but the problem with products on a computer is that if you're multiplying 436 values and they're all really tiny, on a computer, the computer is unable to then distinguish a tiny value from zero, right? You get an underflow error because of floating point precision. And so what are we going to do? We're going to switch to logs. We're going to, instead of dealing with a product that's going to give us a number that's very, very, very small, we're going to switch to logs, and then we'll add up a sum of a very negative number. Okay, does that make sense? So, you know, I mean, that's kind of what we did for the deciphering thing, right? So that's what I'm doing here. I'm going to get the log probability. I've got d beta. This is the beta probability of basically all of our theta values. There's 436 theta values. Okay, there's only one alpha and one beta value, but we're going to get what's the probability of all 436 theta values given alpha and beta, and we're going to take the log of the probability rather than the regular probability, and we'll sum them up. We're also going to add the binomial probabilities of getting y hits out of n at-bats, okay, assuming that you know, the probability is determined by theta, and there's 436. So each of these things is a vector of 436. There's 436 y values, 436 n values, and 436 theta values here for determining the binomial probabilities. We're going to get 436 binomial probabilities. We're going to take the log of all of them, and we're going to sum all of them up. Okay, and so this would be the equivalent of taking the product of all of those numbers, but now we've summed them all up. Okay, and so now we have a value that's proportional, or I mean, that's the log of something proportional to the target distribution. Okay, so technically, we would, you know, there's a constant for the prior alpha and beta, but you know, we don't have to worry about that. Okay. All right, so in the sampler, this is what we do. I'm going to do 15,000 iterations. It'll take a while, and each iteration I have 436 theta values to estimate, plus an alpha and plus a beta value to estimate. I've got 438 different values to estimate. And so fortunately, we can use the Gibbs sampler to draw random values of theta from the directly from the conditional distribution. Okay, and I'm hoping in homework 5, when you compared the multivariate metropolis versus the Gibbs sampler, I don't know, you saw that the Gibbs sampler is a little bit more efficient in terms of drawing values from the target distribution, because you're drawing directly from that target distribution, just conditioned on the other values. And we're doing the same thing here. Okay, so we are drawing the values of theta. Otherwise, we'd have to propose a vector of 430, you know, of dimension 438, which would probably have a very low acceptance rate. here we're going to propose the values theta one at a time, all 436 of them, okay? Then, or not propose, but just draw them, okay? We're going to propose alpha and beta using our propose function. So this will be a random normal value drawn from alpha and beta. I'm going to increase my standard deviation to 6, something a little bit bigger. And the first value that returned by propose will be A prime, and the second value will be B prime, okay? And so the log ratio, the ratio, I guess the log ratio, is going to be basically the probability of the proposed divided by the probability of the current, okay? But because we're dealing with logs, instead of probability proposed divided by probability of current, it's going to be log probability of proposed minus log probability of current, okay? And so that's going to be, I guess, my log ratio. And then after I do that, I will draw a random uniform value, u from our unif, and if the log of u is less than the ratio, then we will set alpha and beta to be our proposed A prime and B prime values. And if not, this step will not happen, and we will just keep the current values of alpha and beta and store them into our matrix A, B, into row J. Is that okay? And that's the sampler. So you've got Gibbs steps up here, a Metropolis step here, and we're going to calculate values for all 438 parameters this way. And it's going to take a little while to run because I'm doing 15,000 iterations. Every single iteration is calculating 438, or sampling 438 different parameter values here. So we'll let it run for a little bit. Are there any questions? This all makes sense? We're all good? Okay, so I finished running, and we can see, so the first column, AB column 1, is going to be estimates of the alpha value. Okay, and so we can see, in the beginning we started off terrible, and so it moves up, and I don't know, somewhere around here, I don't know, we're drawing a bunch of values. I could probably improve my proposal distribution, but this is what we have. And if we look at the plot of beta, it almost looks exactly the same as alpha, okay? Like when alpha goes up, beta goes up. When alpha goes down, beta goes down. But they are different values. Well, you can see that the scale on the y-axis changes, okay? And we can kind of create a histogram of the values. I should probably throw away like, I don't know, the burn-in, I don't know, maybe throw away the first 3,000 values or something, okay? So we'll throw away 3,000 to 15,000, or I mean, we'll only keep 3,000 to 15,000, okay? And so these are likely values of alpha, anywhere from 120 to 160-ish, something around there. Likely values of beta, I don't know, somewhere from 300 something to 400 something. Okay. If we ask, what is the mean of all of these values versus the mean of all of these values? Okay. Mean value of alpha is around 140. Mean value of beta is around 392. Okay. Okay, let me just show you. So this is technically not, this is just an estimate of what alpha is, okay? And this is just an estimate of what beta is. Technically, if we were Bayesian, doing a true Bayesian thing, we would consider all possible values. But I just want to kind of show you what if we use these point estimates of 140 and 392 as estimates of alpha and beta. This is this is what the beta prior would look like if we used maybe I should do 139. Okay, if I use 139 and 392 for alpha and beta, this is what my prior distribution would look like. Okay. From the homework, we used values 81 and 219, and if I plot that, we see it looks almost exactly the same. The homework distribution is a little bit wider, and ours is a little bit more narrow. But basically, you know, in the homework, when we created our prior distribution, we were just kind of using our gut feelings and whatnot, and we produced this prior distribution. But this tells us that we weren't too far off when we try to estimate what alpha and beta is by including them as random variables within our model. We end up getting something that is, the numbers are bigger. But if we look at the ratio, we can see, 139 divided by 81, it's about 1.7 times bigger. 392 divided by 219 is about 1.79 times bigger. So they are, reasonable, okay? 81 divided by, so the mean of is alpha divided by alpha plus beta. The mean of the one given in the homework is a 0.27, and the mean that we're estimating here, 139 divided by 139 plus 392. Okay, the mean is a little bit lower at 0.26. Okay, and this explains why we see such strong correlation between the plots of alpha and beta. So they look almost identical. And what we're seeing is that, what would happen to the resulting distribution if instead of using 139 and 392, if they went in different directions, right? So if I increased alpha by, let's say, 10 to 149, and instead of decreasing beta, instead of also increasing beta, I decreased it to, say, 382, okay? If they went in opposite directions, what would happen? The distribution shifts, okay? So let me just show you. So we had 139 versus 392. So if you bump one up too much, or if they move in opposite directions, then the distribution shifts a little bit too much for what the sampler is comfortable with. Okay, versus even if I increased both by, let's say I increased this one by 20% times 1.3, what is 139 times 1.3? 180, and 392. So here I can add basically 40 points to this, and if I do 392 times 1.3, I'm adding 100 something, 510, okay? The resulting distribution is looks very similar. It's just a lot thinner, right? Whereas changing how they, because of their kind of, the values of alpha and beta basically determine where the mean is. If you move them in opposite directions, that's going to significantly shift where the mean is. Whereas if you change them together in a positively correlated manner, then it will not shift where the mean is, and it'll just kind of shift how wide or narrow the distribution is. And so that, to me, that explains why we see such strong correlations. And probably that means for my proposal distribution, I can probably significantly improve by proposing only values of alpha and beta of A prime and B prime that are highly correlated. Okay, and so if I draw think RMV norm, oops. So I want to draw RMV norm. I want one value where the mean is going to be equal to alpha and beta, and my sigma matrix will equal R bind. Let's do 1 comma 0.95 and 0.95 comma 1. Okay, and so this will only propose values that are highly correlated. So let me this is a little bit silly that I've got to do it this way, but I think so. This will be my proposal, and there we go. Oh wait, hang on, stop. I'm going to just reduce my k to something a little bit lower. K will be 6,000. Okay, so we'll let it run. All right. Is this switch okay, what I just did? So here, my initial proposal distribution was I propose a random alpha what am I saying? Oh, you know what? I probably need my sigma to be larger. But my random alpha is, I'm proposing my random alpha independently of my random beta. Okay? And so so only values where alpha and beta happen to be correlated will be accepted. Okay? Now I'm saying let's propose only values that are correlated, because that's what we see here. So anyway, let's just take a look. Oh, you know what? Yeah, I think my proposal, for my proposal I need, I apologize. I want to probably increase something. Do I do 9.5 here? Just want to see what happens when I do that. Okay. Yeah, that seems more reasonable. So we'll do 10, 9.5, 9.5, and 10. Okay, this is going to be my proposal function. So now we're only proposing values kind of like this, and then we'll run this, let it run. Okay, so these are kind of different values of alpha and beta that we get, again, highly correlated. But here we already started off at a decent value here. So the mean, yeah, we're getting something around the same value. 138 and 390-ish. Okay, so not a whole lot of change between by changing up our proposal thing, but maybe we're getting something a little bit more efficient. Okay, I can and basically these are kind of all the different values of alpha and beta that we could use, kind of this being the highest, but you know, as low as on the lower end or up on the higher end. These are all just very highly correlated things. Okay, this could work also if we take a look at the rat tumor data or something. So so for the baseball, because the batting average window is so small, it requires the values of alpha and beta to be highly correlated. Okay. If we go back and look at the rat tumor data, I've got 70 values of Y, 70 values of N, and we can do basically the same thing. Okay. This is the distribution of all the different proportion values that we observed in our 70 different experiments. Okay. So a lot of our rats, in a lot of our experiments, very few rats developed tumors, and in some of the experiments, you know, over 30% of the rats developed tumors, but not that many. Okay, so our density here looks something like that. So in this case, I'm going to just continue using my original proposal distribution here, and we'll use the log probability, and we'll go ahead and run a few iterations here. Whoops. Did I do something? Oh. Okay, that's fine. Okay, so we'll let this run, and we will take a look at the resulting plot here. So here we have fewer parameters to estimate, only 70 experiments, so we've got 72. We have the 70 theta values plus an alpha plus a beta, and this is kind of the trace that we get here. So there's you know, a lot of correlation between the values as well, and these are kind of the different values of alpha and beta that we see, and we can see kind of what the plot looks like. So we got 2.72 as a mean, and 16.4 as a mean here. So that's kind of what the prior distribution might look like if we create a kind of a histogram. We see these are kind of the likely values of what alpha and beta would be to use. So you know, general higher concentration somewhere around here, but the alphas and betas could even be higher or lower. And that seems to align with what our our empirical distribution on alpha and beta appear to be. Okay, regarding, you know, what proportion of the rats would develop tumors. Okay, I'll post this code and you guys can take a look at it. I've got there's another neat application, I think, of Gibbs sampling, which is quite powerful, and we'll take a look at it next week. It's going to be we're going to use Gibbs sampling to help us classify documents. Okay, we're going to estimate the parameters of our I don't know, of the model using Gibbs sampling, and we'll use a kind of a naive Bayes classifier to classify the documents themselves. And I think it's pretty neat because when we're doing just these toy examples, we might not realize how powerful some of these methods are, and so we can get a glimpse of it. I'm hoping to give you a small glimpse of it next week. Okay, I'll work on writing up that test 3 and homework 6 and release that to you guys. And all right, so have a great weekend. We'll see you guys on Monday.
So next week we're going to use